Come on, man. Come on. Don't do me like this.
I didn't even laugh, okay?
That look was enough.
Okay.
I'm joking. You're good. You're good. Don't even worry about it. Okay. Alright, guys. So today we're going to be doing chemical kinetics. This is the last topic for general chemistry. This is a very simple topic. Pretty much what kinetics means is rates of reactions. So let's get right into it. Okay, so the first question here says, what is the subject of chemical kinetics? Is a study of reaction rates. Okay, kinetics is usually some type of movement, and chemical, imagine chemistry. So how do different concentrations affect the rate of reaction, stuff like that. So what is chemical kinetics? The reaction rate. Okay, so how fastly does A turn into B? Or if I increase A, then what happens to B? Does it go up? Does it go down? Or does it stay the same? Okay, how can we define reaction rate? Reaction rate is the speed at which reaction takes place. So if we have a higher reaction rate, then we have a higher speed of product formation. And we're going to get into a bunch of examples of this. What types of reaction do you know? I'm going to split this into like two separate parts. So types of reactions. Okay, here we're going to do orders of reaction. Okay, which we have 0, first, second, and don't worry, we're going to get into them. And here we have average, instantaneous, and initial. So what do these mean? They're written here as well. Okay, instantaneous, if you guys are good at math, remember derivatives. If not, I'm going to draw a graph for you, okay, to understand this. So okay, so this is the first graph. This is the second graph, okay? But let's do this one first. So this is what type of graph? We know this, linear, okay? When we want to find the slope, it's y2 minus y1 over x2 x1, okay? Which can also be written as difference of y over difference of x, which gives us the reaction rate, right? How fast or how slow does this decrease? Okay, so this is very self-explanatory, and the rate will be the same all throughout. But now we have a line that is not linear, an exponential function. Okay, exponential function. Okay, so if we have the rate here and concentration, for example, or whatever, it doesn't really matter for this example. As the rate at initial, for example, initial is here, this is final, you see that the slope of the line changes. It's not perfectly linear. Now, what we can do is using derivatives, right? Or instantaneous. Imagine instantaneous is just instant, right? So, for example, at this particular point, at that particular point, what is the rate of reaction? So we use derivatives. You don't need to know how to calculate this, but it's something like this. And it finds a slope at that particular moment, right? Initial is at the beginning. We know what that is. And average means, for example, the average here would be the same throughout. But the average here, you'd have to take all of these instantaneous, add them together, or initial minus final, and find the average. Okay, so that's just definitions. Then we're going to talk about what is the order of reaction, right? So we said 0, 1, 2 was what we're talking about. And we say 0 first, second order. And it indicates how the chemical reaction depends on concentration of a particular reactant. So if we were to increase or decrease in this chemical formula, okay, either A or B, which are reactants, okay, how does this affect the products? Okay, and this is kind of like a puzzle, and it's very easy to do, and we're going to be doing a bunch of examples to solidify your knowledge. All right, so here, this is a longer way of saying what is chemical kinetics. So it's the area of chemistry concerned with reaction rates and the sequence of steps by which reactions occur, right? So what did we talk about? What is chemical kinetics? We said it's a study of reaction rates with concentration over time. Okay, so just remember, chemical kinetics is study of reaction rates, which in simpler terms is movement of concentration over time. That's it. Okay, so just think of it as study of reaction rates. Now, what is the reaction rate here? What did we say? We said it's the speed at which a reaction takes place. What does it say here in a longer version? Either the increase or the decrease, either the increase in the concentration of a product per unit time or the decrease in the concentration of a reactant per unit time. So what does this mean? If you increase, right, the product per unit time might increase or decrease. What does that mean? If you increase something, then that same something, okay, over time increases. Let's say, for example, m over s, which is equal to velocity, okay, increases. That is just a speed, right? So if I increase, for example, this guy, right, then this is going to move the reaction this way and increase the speed of the reaction to make more products, depending on the order of reaction. This is super important, okay? Now, we're going to be defining the types of reaction rate again, just as Uni of Debrecen definitions. Here we talked about it right here. But let's just repeat it. So the average reaction rate is the change in the reactant product concentration over a change in time. The rate slows as reactants are used up. So how do we calculate it? Fine. Really, really large point, like on different ends of the time. So big difference in t, and we find the average. This is indicated by this box here. Okay? Then we have instantaneous, which is the rate of time t is obtained from the slope of the tangent on a concentration time curve at time t. If you're not good at math, just think of it as this little blue box, triangle. So we want to know the slope right here. So we take the tangent here, okay, to know that exact instant slope, okay? That's all you need to know about it. Then, lastly, we have the initial rate, which, what do we know about the initial rate? It is right here. Okay, so again, we take the instantaneous rate at the beginning. Okay, that's all. All right. So here it says, give the average and instantaneous rates for A and B. So what is the average? We said just normal slope calculation, big difference in time, right? So difference in time over difference in concentration. Now, this is a derivative function, okay? Usually it'll be dx over dy, okay, equals v plus or minus, okay? Depending on whether the line is like this or like this, okay? Either if it's increasing or decreasing. Don't worry too much about the sign. But so we know that a derivative gives us the instantaneous velocity at a certain concentration, right, per unit time, and it's made by this equation right here. And a good way to remember it is So you have your variable concentration over time, because on a graph it looks something like this. Concentration, time, right? And then we put the d in front of it because derivative. So d concentration over d time, right? So dy over dx. Okay, perfect. And again, the plus or minus depends on which way it's going. So if it's decreasing, right, on the graph, then that's a negative slope. If it's increasing, then it is a positive slope. Okay, here we have a question saying choose the incorrect formula of the reaction above. Okay, so what does this mean? This wants the instantaneous reaction rate. How do we know this? We have d. Okay, so it wants the derivative. Okay, and to take you through how I would think of this, because University of Debrecen always puts like wrong answers in the multiple choice that like you might think is right, so go through every single one. Okay, one thing I want to mention, if you see a negative, that means they're on opposite sides of the equation. So for example, we have CO2. Okay, so it goes right here. Okay, so we have CO2, there's no coefficient, that's good. And we have Br2, which is here. Okay, and that's also good. There's no coefficient and it's negative because it's on a different side, so A is good. Then we go Br minus. So let's draw. Br minus is here, okay, right? Has a 2, so remember the 2. And the H plus is on the same side, but it also has a 2. So if we have a ratio 2 over 2, what does that equal? 1, so you don't need to write anything, okay? So this is also good. Then we have C. So we have HCO2H, okay, right? So no coefficient here, it's all good. And then Br2, not negative because it's on the same side. So these two are also good. Then we're going to check D. So we have HCO2H, okay, that's good. And then we have half of H plus. So it's good that it's half because this is 2. So we have 1 here and we have 2 here. So what does that mean? 1 over 2. Okay, which is good. We have it. But this is on the other side of this symbol. So it's actually a product. So it has to be negative. There's a missing negative sign. That is supposed to be right here. Okay, and let's just check E to make sure. E, Br minus, right here. Okay, there's 2. And then Br2 is all the way here. So to make up for this, we put a negative 2 on the Br2 to make it equal to each other. Okay, so this would be the wrong answer. Everything else is good because it is missing a negative sign. All right, it says list the factors that influence the rate of chemical reaction. These are the main ones. So we have temperature, concentration, catalyst, surface area, collision theory. We're going to get into that. And a last one that kind of falls into the same thing as concentration is pressure in gases. Before we move on, I'm just going to talk about how that kind of relates to concentration. In Le Chatelier's principle for chemical equilibrium, let me just write an example equation, okay? We learned that if the question has not told us any further information, we use the molar coefficients to find out if the reactants or products have the highest number of moles, right? Because as you increase the pressure, the area that has the most amount of particles, in this case the most amount of moles, will increase first, right? So as I taught you guys, this is molar coefficient of 1, molar coefficient 1, I'm just writing it in this case, and this is 1, 2. But delta N equals what? Sum of moles of products minus sum of moles of reactants. Okay? Sorry for my handwriting. Now, what does this mean here? We don't necessarily need to know the change in N, but here we know we have 1 and we have 2. So, which was bigger? The 2. So, now I tell you there's going to be an increase in pressure. On which side is going to have an effect? On the side that has the most amount of moles. Okay? Which is 2, right here. Okay? So, if I increase this, the concentration here goes up, deeming everything else as normal, this is going to make a shift here. And the way I like to think about it is, if this side is going up a lot, this is the to product side, and this side stays like this, this is a spontaneous reaction to go this way, right? To balance out the seesaw from this to this. Sorry, like completely balance it out. Right? And that's how the pressure works. So it kind of increases the concentration as you decrease the volume. Okay, so here's pretty much going to repeat what I said, but that's okay. So for a reaction to proceed, the reactants must collide, right? So for A plus B to give C, or C plus D, A and B have to come together, okay? Now, why does not every collision result in products? You might ask yourself. Because sometimes the molecular orientation is not correct or favorable. And the second one is there's not enough energy in the formation of the transition state. Okay, what does this mean? Molecular orientation, let's go over here. So let's say, actually before this, let's say I have two magnets. I have plus magnets and minus magnets. If I do plus and plus, okay, and try to add them together, what's going to happen? Repulsion. But let's say I change the sign to negative, what's going to happen? Attraction. Attraction. Now, what does this mean? This is the same for atoms. Why do I say this? For example, let me just read this for you guys. So what is collision theory? It is the average kinetic energy. As the average kinetic energy increases, the average molecular speed increases, and thus the collision rate increases. So this is the same thing with temperature. As you increase temperature, these molecules are agitated higher than they were before, increasing the collisions, increasing the chance of getting the correct molecular orientation and enough energy to form the transition state for the reaction to go to completion. Now, let's talk about ineffective and effective collision. It's very important. So we have NO plus O3, okay? And we have NO plus O3 here as well. But what matters is what it's bonding with, okay? So if red is red, imagine or blue is blue, imagine these are both positive, okay, magnets. And so are these ones. So they have repulsion, strong repulsion towards each other, and they will not go to completion of the reaction. But let's say these two are now negative and positive. Then when they hit, they will have strong attraction forces towards each other, going to completion. Now, you don't need to know exactly how this works in terms of how each collision and tell whether it's ineffective or effective, but you have to understand that, okay, sometimes when molecules bond, their orientation needs to be favorable for the reaction to go to completion, okay? And energy in terms of, we're going to get into the graph, but for example, let's say there's not enough energy for these two to actually collide, right, to get to that transition state, which is the highest potential energy state. It's not going to work out. It's not going to go to completion. All right, so now transition state, right? So we said, what is this transition state? The highest potential energy. What does that mean? Let's read it, the longer definition, and then try to simplify it. the configuration of atoms at the maximum in the potential energy profile. This is called the activated complex. Okay, so this is either the activation energy, the transition state, transition complex, activation complex, a bunch of names. But what you need to know here is this is where, okay, all the atoms receive the highest energy they possibly can, okay, for this reaction to go to completion, right? We're not going to agitate them too much, but just enough for them to get to their transition state. Why? So that the bonds of the reactants can break or have proper collision, right? Because as we talked about, the collision theory requires energy over here, energy for the formation of transition state to ensure correct molecular orientation, right? So this is where the bonds break and everything else forms. And as they get more stable, they either release heat, becoming exothermic, or become endothermic, absorbing the heat. Okay, so highest potential energy. Imagine the point at which the reaction actually is happening, right? So for example, I want to make sure you guys really understand this. We have, let's say I have Coke and I have Mentos, okay? Having these two in my hand, nothing happens, okay? But I take the Coke, right? And the activation energy is me putting it in, right? Because it's not going to get put in by itself. I put it in, then it starts to fizz up and create substances that I'm not really sure about, like the molecules and all that, but you know what I mean? So it fizzes up, right? And in this is the transition state. And then once it becomes stable again, and we get our product of whatever happened to the Mentos or whatever happened to the Coke, that is the products. So in the moment that the reaction is happening, that is a transition state, and that is that of the highest potential energy. Potential energy is the chemical energy, by the way. Okay, so I hope you guys understand that. Then it says, using collision theory, explain how the concentration of reactants and the temperature affect the reaction rate of reactions. So what do we say? We want to ensure correct orientation of molecules colliding, right? So they go to completion. And another thing is we want to have enough energy for the transition state. How does this work? If we increase, I draw you guys a container, okay? We have a couple particles here, okay? Maybe 30% of it goes to completion. But then I put a bunch of other particles, okay? Increase the concentration. So these two particles are not just going to interact with each other, but a bunch more. What happens? Maybe now 70% of it goes to completion, because these guys are getting in so much contact with each other that there's a higher probability of getting that correct effective collision. All right, now let me draw the same container. Okay, so we have particles, okay, and let's say they vibrate a little bit, right? These guys vibrate a bit, or maybe even they go a little bit this way, a little bit that way, whatever. So relatively, energy for them is low, right? Because what happens here, they're not moving too far. One of their particles moves this much. But let's say I increase the temperature. Sorry for my handwriting, guys. The particles in here are going to be heated up, right? They're going to have a lot more energy stored in them. So they move way more, right? So instead of this guy, they move something like this, right? Because we learned that, for example, this is solid, liquid, and gas, okay? Particle in the solid state vibrates, does not really have motion. Particle in the liquid state has a little bit of motion, nothing crazy. Particle in the gas state Oh, it's very excited, it scatters everywhere, you know. So, as you increase the temperature, these molecules, okay, these little particles are going to be very, very excited. They're going to have a lot more movement. What does that mean? This movement causes more and more collisions. Now, imagine collisions. If I have one collision, what are the chances that I get the perfect orientation for this reaction to go to completion? But imagine if I have 1,000, then there's a lot higher chance that it will go to completion, right? Actually, let me not erase that. Okay, then let's do this question. Here it says, how will each of the following affect the rate of reaction? Firstly, you check, what's it called? You check the states. Okay, that's what I always do, just to make sure what can and cannot increase. Then we check the rate law. So we see that the rate law of CO is not included over here. So that means that it's a zero order, and no matter how much we increase CO, there will be no change on the products or to the products. Okay? Super important that you guys understand that. Now, let's do the example. We have decreasing the pressure of NO2. Okay, so where's NO2? Cool. From 0.5 to 0.25. That means we want to check one thing. Where's the number of moles? Oh, 2 and 2. Okay, same. But it's saying specifically that it's decreasing the pressure of NO2. So this is going down, right? And this is a little up. So what do? This goes back here, right? So how will this affect? This will either slow down the rate of reaction or make it reversible. But probably just slows down, because if you were to have the value for V and K and you plug in the pressure difference, it probably won't change the entire, it won't shift the entire reaction, just like that. Okay, then it says increasing the concentration of CO from 0.01 molarity to 0.03. Now, what did I mention in the rate law? The rate law, I said that it doesn't include the CO. So what does that mean? It's zero order. We're going to get exactly into the math of that. And it's very easy. It's puzzle-like. You'll love it. Now, CO is not in the rate law equation. What does that mean? It does not affect the rate. So no matter what happens here in this, then nothing changes, right? Let me just turn on do not disturb. Sorry. Okay. Nothing happens. So nothing happens. Slower was the first one. Still the last one. Increasing the temperature. No matter what, you increase the temperature, this will increase the collisions, which, what did we say? Increases the rate. So, faster. Done deal. Okay? Now, here we get into the math of things. Okay? Rate law. An equation that shows the dependence of the reaction rate on the concentration of each reactant. In simpler terms, this is an equation written for reactants only. It only say products for theoretical. I don't know why they include it in the PowerPoint, but usually it's only reactants, okay? So it should not have a negative value up top, usually, okay? To tell us what? If we were to, these brackets, okay, they mean concentration, okay? Just remember that. Now, what's M and what's N? M and N, you might think, are the molar coefficients, like equilibrium, okay? But no, I really want you guys to get that out of your head. They have nothing to do with molar coefficients. They will in a little bit later, but that's for a one-word answer, and it'll be not related to this at all. Okay, so remember, M and N are nothing like equilibrium, and they will not have in any way, shape, or form an effect on the rate law. Okay, except a little later, but that's for one specific point. Now, M and N represent the order of the reaction, okay? And we're going to talk about that in a second. Now, the rate law equals, okay, you guys have to memorize this, K, which is a constant, rate constant, okay, concentration of each reactant raised to a power. Doesn't need to be necessarily M or N, but raised to a certain power. And that power you're going to figure out through experimental data. So let's get right into it. Okay, before we get into that, we're going to be talking about the characteristics of zero, first, and second order reactions. Okay, so zero order, that means there's no change. No matter what you do on one side, nothing else will happen on the other side. This is this equation. Now, this looks awfully similar to y equals mx plus b, plus a negative sign because it decreases, right? So that's an easier way of remembering it. Now, first order is an exponential function, right? Because we have something raised to 1, okay? Now, what happens is that you need to take the ln, right? So that we can get a straight line graph, or else it would look something like this. And we can't do anything with that. And second order, same thing. We want to get the line equation of it, so we put it 1 over A, which is concentration of a reactant, okay? Now, this is how you plot it, okay? Because it's multiple choice, I don't think they're going to ask anything like that. This is the rate law equation, if you want to figure something out. And that's all, okay? So, here it says write rate equation for a first order reaction. First order reaction means something, concentration raised to the 1, but we don't need to write the 1, okay? So, this would be V equals K A. That's the rate law equation. And the rate equation is this guy in integrated form. Okay? Again, same thing that's written here. Okay? Now, these are just some things that you have to memorize. They're good for calculations and stuff like that. Chances are they're probably not going to come, or if they come, they're like one question, so I wouldn't spend too much time on it. But there's something that you should know, maybe create flashcards for yourself, stuff like that. Just understand how the rate law works. Okay, and the units. If we go up here, we're going to realize that unit of zero order is molarity over seconds. Then we have 1 over second. Then we have 1 over molar seconds. Okay, molarity seconds. So these are just things you have to memorize. Okay, here. These are some calculation questions. It says here, first, we have 2 reactants, okay? And it says, unit reaction of NO and H2 is second order with respect to NO and first order with respect to H2. So, what does the rate law equation look like? V equals K reactants, so NO, M, H2, N. Okay, how do we figure out M and N? Well, it's actually given to us. So, second order for N2, so you just plug in 2, and H2, you plug in first. Okay, then it says, write the rate equation for this reaction, right, which is this guy. And what is the overall order of this reaction? The overall order is all of the coefficients added together. So 2 plus 1 equals what? Equals 3. So the overall, therefore, the overall order of reaction equals 3. Okay, that's how you solve that. Now, we're going to do this question. So this is, what is the order of the reaction with respect to each substance in the rate equation? So the order here, because it's not written, is 1, and this is -½ Okay, that's the order. What happens to the rate of reaction as SO3 increases? Again, as I said, usually you don't write products in the rate law equation, okay? But they did here for theoretical example. So as I increase this, what happens? I'm going to shift backwards, just like equilibrium. So it either slows down the rate reaction, or even, depending on the amount of concentration, result in a stop or start of the reversible reaction. All right, so that's that. Here, it says, what is the order of the reaction with respect to each substance in the rate equation? So it wants us to say each one. What is it? Okay. Again, here they wrote the product, but they're not supposed to do that. So H2 is 1, 3/2, -1. Okay, so that's each one of those with their respective molecule is the order of each. It says, what happens to the rate reaction as the concentrations of H2 decrease and HBr increases? So these two, they have a positive order. Okay, so as in, if you add concentration to them, what happens? V increases, which is the velocity, the speed, the rate of reaction, right? So as you decrease them, okay, you increase this, what happens? You get a cycle, it goes whoop. So same thing as here, okay? It either slows down or what's it called? Slows down, or can completely stop it or make it reversible. Then what is the overall order of the reaction? You simply add all the numbers up. Usually you wouldn't have this -1, but for this case you just add it all. Okay, here comes the math. So I want to speak about ratios. Let's go right over here. We have 0 order, first order, and we have second order. Now, let's say we double concentration, okay, for each. Okay, so if I had 1, right now for all of them becomes 2, with nothing else changing, okay? 1m to 2, okay? Not important. But what does that mean? We multiply by 2, okay? So plus 2 is our, like, relativity spectrum, right? Then for 0 order, what happens to the product? Concentration, or the rate, okay? What happens is nothing changes, okay? First order, it also multiplies by 2, the concentration or the rate. But second order, it multiplies by 4, right? So 2 squared equals what? 4. Or if it was 3, then 3 squared equals 9. And that's a second order reaction, okay? So that's something I want you guys to understand when doing the puzzle portion of chemical kinetics. So this one is a pretty tricky one, but let's get right to it. So it says, given the following experimental data, find the rate law in the rate constant of the reaction. So what is the rate law here? We have 1, 2, 3. Let's write it out. V equals K. Don't forget K. And O M, we're going to find it, NO2, N, and O2, L, okay, L. Now, we got to find something that the other two are constant in to only isolate for one concentrate change, okay? So, for example, 1 and 2. So, see that here multiplies by 2, okay? Nothing else changes, which is good. But since nothing else changes, we then have to look at the initial rate. How does it change? So, got multiplied by 2. So, if you multiply by the concentration by 2, the initial rate goes up by 2. What is this? 2 over 2? Proportional, right? So, it's first order. So, for the NO, you write 1. Okay? Then, I want you guys to think, what would be the next step? So, to isolate for this guy or for this guy? For the NO2, we can actually see that there isn't anything that keeps everything else constant. So we can't do that one just yet. But for the O2, there is. There is 1 and 4, right? 1 and 4, nothing changes here, nothing changes here. Oh, we have times 2. Okay, nothing changes in these two, so we have to look at initial. Oh, the initial doesn't change. So what happens? 0 order. What does that mean? 0. Anything to the power of 0 is what? 1. Just take it out. Sorry. Okay. Now, we understand that O2 will not have any effect, so we can absolutely disregard this. We can focus on 2 and 3, since these two are constant, right? So we don't need to worry about that. And we have this times 3. Okay, so we have times 3. Everything else is constant, so we look at the initial rate. The initial rate goes from 4 to 1.26. Make sure you understand the exponents, okay? Here in an exam, don't do this yourself. Put this in a calculator to avoid mistakes. And this will give you a multiple of 9. So you do this guy divided by that guy, right? Which gives us 9. So we have 3 raised to x, for example, gives 9. What is x? 3 to the 2. So that is second order. Okay, so erase all this. So n is actually second order. And now, just to add on, what is the overall order? The overall order is 3, because 1 plus 2 equals 3. Now, let's say you want to find the k constant, okay? Some calculations. I don't have my calculator with me, so I can't actually find it, but I can tell you how to do it. You plug in one of these values, okay? Because we know v, for example, let's do number 1. V equals 2.1 times 10 negative 2 meters per second, okay, equals k. We have the concentration of NO, which is 0.1 to the 1, so we don't need to write that. And then NO2, which is 0.10 m to the 2. You multiply these two, bring it to this side, divide it, gives you k. So that's how you find the rate constant. Okay, so defining half-life. What is half-life? Let's say I have a full chocolate bar. Okay, there's 4 pieces on each side, so 8 pieces in total. Once this chocolate bar reduces to a half, okay, so only 4 pieces are left, that's the half-life, okay, decays by half. Very simple. Now, different things are independent and dependent. So, what does that mean? If we look at the equations here of the half-life, this will show you, by the way, this can be written as ln 2 if you can remember that instead of 0.693, okay? So, to see what is dependent and what is independent of this, we see that, does temperature have an effect here? No, it doesn't. Here, does concentration have an effect? No. How about here? It does, okay? So we have to understand that. Okay. And these are how you calculate it. You plug it in, okay? Little thing to remember, if you were to take the ln of this guy, this also becomes a linear graph. Why am I saying this? Let's say you're in an exam and you freeze up. It says it takes 30 seconds for a first order reaction to get to its half-life from 80 to 40. Okay? Because we could turn this linear, what does that mean? That means that each 30 seconds, it decreases by half. So the next one, what would it be? 20, then 10, okay? But something you need to understand is they will never go to completion because you can never do divided by 2 to the point where you get to 0, okay? But for the second order, it increases. So, for example, it'll decrease, for example, 40, then it'll decrease more and more and more. So it's more useful to use the equation. With the first order, you could work it out common sense wise. So here it says the decomposition of, Here it says decomposition of N2O5 is a first order reaction. So 2N2O5 gives 4NO2 plus O2. The rate constant is, it gives it to you, so that's your K. And it says calculate the initial rate of the reaction if the initial of N2O5 is 0.25. So it gives us the first order, gives us this. You guys know how to do this, okay? It says calculate the half-life. So first order reaction, we come here, use this. So ln 2 over K equals half. And we come here and calculate it. Then it says how long will it take for the reaction to consume 95%, right? 95%, you have to calculate that 5% is left, okay? Because 1 minus 95% equals initial amount, right? So how do you do this? You do 0.05 times initial concentration gives you that, okay? And then you take this guy and then you plug it into the formula to find T, and that's it, right? Then this is very similar. I'm not going to do this. It's the exact same thing pretty much. Here as well. Again, this is just calculation questions. Okay. Here it says it's true and false questions. Okay, it says the half-life of the first order decomposition reaction of N2O5 is 18 minutes. Are the following statements true or false? So first order, that means every 18 minutes it will half, okay? The reaction goes to completion in 36 minutes. No, it does not. It cannot go to completion, okay? Why is that? You divide any number by 2 a million times, you'll never get to 0. False. The quantity of remaining N2O5 after 36 minutes is half of what remains after 18 minutes. Let's read that again. The quantity of remaining N2O5 after 36 minutes is half of what remains after 18 minutes. So this is 18 minutes. Okay, so this is 1 over 2. Then 36 minutes. This is exactly half of this guy, right? Because we know that it's proportional. It's first order. True. It says the same quantity of N2O5 is consumed for every 18 minutes. This is false. Why? It's not linear. Okay? Yes, the half-life is always X amount, but it goes half of the initial, then a quarter of the initial, then an eighth of the initial, then a 16th of the initial. Keeps going. Last question, it says 1/4 of the original quantity of N2O5 is consumed in the first 9 minutes of the reaction. That's true, because in 18 minutes, half of it goes away of the original quantity, so a quarter is gone in 9. That's proportional, true. And you can see over here, you have 1, 0.75, 0.5. This is the halfway mark of 104. Okay. Okay, so now we're getting into elementary reaction. This is where I said the coefficients of molar ratios matter. So the number in front of the element or molecule in a chemical formula start to matter. Quick thing, if and only if you use this, if they say it is an elementary reaction. If not, you do not touch. Now, if there's 1 or 2 of the same thing, they're different. 2 is 2. 1 is 1. Okay, might be very easy for you, but know it. A plus B, it's how it's written, whatever. Now, at the end of it, the number of it responds to the molecularity. Molecularity is just classification of elementary reaction based on number of molecules, and that's it. So, overall order 1, unimolecular. Overall order 2, bimolecular. Overall order 3, thermomolecular. Okay? Just something you gotta know. It's very easy, right? And that's because elementary reactions are individual molecular events. They happen as that. There's no intermediates, there's no catalyst, nothing. It just, this becomes this. Okay, give the rate laws for the following elementary reactions. You see this? Elementary reactions. It says unimolecular reaction. So, this is the reactants, this is the reactants, this is the reactants. What does this equal? V, well, it's already written K. V, so K, O3, 1, we don't write the 1. K, O3, we don't write the 1 again. Okay, and last one, we have K, O, but look, we have 1, 1 equals 2, right? So 2 and M. Okay, that's all. Super easy stuff. Then we move on. The overall reaction for the decomposition of H2O2 in the presence of H3O and Br minus. Okay, so here it says it consists of 2 elementary reactions. What are the molecularity of these reactions? Exactly what we did before. So there's 1 here, there's 1 here, there's 1 here. This is thermomolecular, and you write it like that. There's 1 here and 1 here. It's bimolecular, and you write it like the way we just did in this. All right. So this is just some practice for you guys, understanding how to write the elementary reactions. I'm not going to go through this. I feel like it's very self-explanatory. Do it if you need to, but you see CO2, there's 1 in front of it, so you write a 1. Okay, done deal. And then you see which ones are right, which ones are wrong, right? So CO1, that's correct. CO2, 3/2, that's wrong, right? So which of these following could describe elementary reactions? This is false, stuff like that. Because this should have been an overall order of 2. Okay? Sorry guys, I know this video is long. Okay, so multi-step reactions, only thing you need to know is, let me put it to you guys in terms of an analogy. So, you have race car, you have old car. does not go fast. Okay? Both of you guys decide to drive together and go to Budapest. But you have to keep up with each other. Is the old car going to miraculously become fast and go with the race car? No. You have to go at the speed of the slow car, right? So the slow car is a slow step, and what do we call that? It is the rate determining step. Okay? So slow determines the speed at which is the fastest that it can go. Okay? So whenever we're using that as the elementary step or whatever, that is what we use to make the rate law. And you can see that over here. Same way as before, the elementary step, but now you just use the slow step to do it. Okay. This is how to kind of see this in a question form. So I want to show you guys. Sometimes in the question, it's written fast or slow. Okay. So fast, slow. Or it'll give numbers 70, 70, 30. All right. What does that mean? All right, sorry guys, my phone ran out of storage. So here, I mentioned how the different ways of speeds can be written, either slow and fast, and they tell you, and that's really easy, or they'll give you in K. So if the rate constant is higher, then what does that mean? It's faster. So which would be the rate determining step? This guy. Okay. And then the overall, what is the rate equation for the overall reaction? Also this guy. What is the rate determining step? Also this guy, which is step 1. Okay. That's all. Experimentally, okay. Evidence suggests that the reaction between NO is a two-step mechanism. Sure. I want you guys to learn one thing. So there's catalysts and there's intermediates. This is how you do it. Catalysts, you have to identify, or intermediates. Catalyst will appear as a reactant and finish as the last step as a product. An intermediate will show up as a product. Then next step be a reactant. Okay, so NO3 here is a reactant. Okay, NO2 gas is a catalyst. Okay, that's how that works. A reactive intermediate is formed in one step and consumed in the next step, right? So that's what I'm saying. So product then becomes a reactant. All right. Here it says the mechanism of a reaction is shown below. What is the overall reaction? So that's the slow step. You guys know how to do it. Which compounds are intermediates, right? So I wonder if that's my writing. No, it's not. Okay, so the intermediates would be this guy, and this guy, this guy. Okay? Then it says predict the rate law based on this mechanism. The rate law would be this guy. So HCOH and I, and the rate, right? So like written like this, and it is a second order because 1 plus 1 equals 2. Sorry, that's 3. 2. All right, test questions. Yay. Okay, this is like the first part of it coming to an end. All right. So I'm going to quickly take you guys through how I solve them. So it says find the wrong answer for the decomposition of HI, hydrogen iodide, that allows second order kinetics. 1 mole of HI yields 1 mole of I and 1 mole of HI. Yeah, because there's 1 and 1, right? So boom. The rate of this reaction depends on temperature. It always depends on temperature. The initial rate of this reaction is higher than the rate measured after 2 minutes. Right, because the rate decreases because it's doing something. The half-life of this reaction is constant in time. Okay, so I'm going to put a little question mark. If the concentration of HI was doubled, the reaction rate would increase 4-fold. This is true because if I said 2 to 2 equals 4 times 4, that's second order, right? So times 2, but then equals times 4, that's second order. The half-life of the reaction is consistent in time. No, because I know that it's exponential. Okay, so this would be wrong. So test question 2. For this reaction, 2A plus 3B plus C gives products. The rate reaction is, we don't have enough information. Why? It's not saying it's an elementary step. Next question. For a certain first order reaction, it is found that it takes 156 seconds for the concentration of a reactant to fall from 0.1 moles molarity to 0.05 molarity. How much time would it take for the concentration of reactants to fall from 0.05 to 0.025? Now, we have a first order reaction. What does that mean? The time stays consistent and the amount just halves. Okay, we know this. You can use the equation. I don't use the equation for the first order because I just know it. So the time from this to go half is 156. So the time from this would also half, which equals 156. So A. Sorry, that's making me a little OCD. Okay, says which rate law has a molecularity of 2 for an elementary reaction? So now it's saying it's an elementary reaction, so the overall order has to be what? 2. This is 0, this is 2, this is 3, this is 1, this is 3. So the only one that works is B. And lastly, it says, given the following rate law, how does the rate of reaction change if concentration of Y is doubled? What does it give us? It gives us the rate law equation. What is the overall order? 1 plus 1 equals 2. So if this increases by 2, then it will increase by a factor of 2. Okay? Done deal. Because this is first order and this is first order. So if this Y is doubled, then that will be doubled. But this is not a second order on its own to be 2 because times 4. So it's just A. Okay? Now we're going to get into the second part of chemical kinetics. Chemical kinetics is a huge topic. That's why it's taking so long, and I apologize for that. But it's extremely important. This is the one topic that I think the seminar questions are actually important to go over because they might pick from this bank. So, how can we define the activation energy of a chemical reaction? It is the minimum amount of energy to make this thing work. Activation energy. You don't have this, you have no transition state, nothing works out, okay? So, if I want to put the Coke in the Mentos, what happens? I need to put energy as the activation energy to put it there. Done deal, okay? And how is it represented on the graph? This, okay, is activation energy. Okay, we're going to get into better examples of it, right? And it says, the collision energy as there's high temperature will increase, and the frequency of collisions will increase as well, okay? Here, question. The activation energy for the reaction is 179 kilojoules. Okay, construction activation energy diagram for this reaction. Okay, no problem. So, it says delta H is 9.5 kilojoules. What's delta H? Delta H is the difference of this and this. Okay, this is delta H equals 9.5 kilojoules. Okay, understand that. This is activation energy, which equals 179 kilojoules. Okay, that's done. Then you go down. It says the activation energy for the following reaction is 9.6 kilojoules at 25 degrees Celsius. It says calculate the reaction heat when the respective delta H values are 33.2 for NO, 90.25 for NO, for NO2 for NO, and 142.7 for O3. Okay, so what is this telling us? It's telling us what's here in terms of energy, and it's telling us how to find the difference. And it's saying that this complete thing is the EA, which has an activation energy of 9.6 kilojoules. Okay, so then it asks you a couple questions. Is the reaction exothermic or endothermic? So we have reactants, products. As we lose energy, what does that mean? Delta H equals negative. So, exothermic. Okay? Then it says spontaneous or non-spontaneous. So, this is a spontaneous reaction with low activation energy, right? How do we know this? We do TS, and that's all, right? Yeah, so this is it. Delta H minus TS. And we see here as well how this works. Okay. I'm just making sure there's nothing I didn't say for this one. Okay. What is a catalyst? It makes the reaction easier. How? Think of it in your head. Imagine I have a dispenser to put the Coke, to put the Mentos in the Coke. Instead of me having to grab the Mentos, bring it there, it makes everything easier, right? So, it makes the activation energy lower. If this is normal EA, with a catalyst, it looks something like this. So we have this, and we have this. Makes it a little bit faster too. Okay. So, it says compare the decomposition of H2O2 molecule in the presence of absence of a catalyst, right? This is normal activation energy, right? If we had a catalyst, though, this would be a little faster and a lot lower activation energy, okay? Here it says identify the catalyst in the following chemical process. I said a catalyst is something that appears in the reactants and leaves in the products, right? So it does not change, nothing happens to it. It just makes everything faster. Here you go. Okay, that's it. What is an intermediate? This guy. Okay. That's all it is. Very simple stuff. Here it says in the overall chemical reaction, A plus B gives AB. Red spheres represent A molecules, blue spheres represent B molecules, and yellow spheres represent the third substance, C molecules. Why doesn't C appear in the equation for the overall reaction? Because it's consumed in the first step and regenerated in the second step. So it's a catalyst, right? So if these are the steps, right? We said yellow, right? It's always there, and it ends up. So we said here, consumed, put out, okay? Does not participate in the reaction itself, like it doesn't like undergo the reaction, but it just helps everything become easier. Catalyst, imagine, makes everyone's lives easier, everything goes to completion. So we have homogeneous and heterogeneous catalysts. We know what homogeneous is. You can only see one thing. Heterogeneous, you can see multiple things. Usually it's solid, in a liquid, whatever, right? So homogeneous is really hard to separate these catalysts, right? But heterogeneous, you can do this very easily. Why? You could see it, solid, you could get it out, stuff like that. It says, which species is a catalyst and what type of catalysis is occurring in the reaction, right? So, I know the answers right here. Don't look at that. But what is something that's consumed and then put out, right? That goes through the reaction. Boom, right? Is it in the same state as everything else? Yep, it's a gas. So it's homogeneous. All right. Here it says, what type of catalyst is it? The platinum in a car's exhaust that catalyzes the conversion of CO into CO2. Heterogeneous. You can see multiple things. You know what I mean? So that's it. Okay, so what are the main characteristics of enzymes? A lot of people told me that the only thing that's important here is to know that enzymes are catalysts and they make everything easier by helping things bind and collide better. But I'm still going to go through it just in case there's one question that we need to know about, and that's it. So I'm going to go over the main points. So What are the main characteristics of enzymes? They are catalysts. What are catalysts? They lower the activation energy. They make everyone's lives easier. You don't need to know this. They're not going to ask that. Or at least I don't think they will, because that's not a good question to ask. Substrates is converted to products in the active center of the enzyme. So what does this mean? I have an enzyme. Okay. Substrate here comes, binds here, goes through reaction, then comes out as a product. Okay. And it makes everything easier because it's like a point where everything can react. Okay. There's two models. There's lock and key model. So it fits perfectly. An induced fit is, it's going and then it shapes to it and grabs it tightly. But it's not like it's like a kind of perfect fit that grabs on tightly. Lock and key is like just a perfect fit. Yeah, that's it. Then we have the free energy changes of the enzyme catalyzed and uncatalyzed process. So here it shows this is the activation energy in uncatalyzed. Then this is the activation energy in with the enzyme. So catalyzed, and it's a lot lower, makes it a lot more spontaneous, right? Because we have this difference. So it's a negative G value. And then it says here, enzymes decrease the activation energy. We can see that. Okay. Then it says, but do not change the equilibrium of the reaction. What does that mean? Equilibrium, we said, is the equal rate of forward and backward reactions. So it may do something to where this goes to there or this goes to there easier, but it will not change the concentration. Therefore, the rate at which this happens at is the same. Okay, so enzymes do not change the equilibrium of the reaction. So it says, what are the key features of enzymes? Imagine there's so many enzymes. They're very specific. Okay, if you have an enzyme that looks like this, it cannot bind to something that looks like this. Okay, has to bind to something that looks like this. There's a high yield, high efficiency, large turnover, regulated action, and often requires small ions. The only thing you need to know here, they're catalysts and they're specific. Also, if we have a graph here on the efficiency of the enzyme, so efficiency of the enzyme, okay, it will look something like this. And temperature, it will increase and then start denaturing because it will actually start ionizing and hurting the enzyme after a certain point. How are enzymes named? We have, you don't really need to know this. I really don't think you need to know this, but imagine ACE. So if it says pepsin, right, or trypsin, we have that, then we have ACE. Some examples are tyrosinase, right? So it makes that urease, stuff like that, right? You don't need to know it. I really don't think you need to know it. But just remember, if there's an ACE, it's probably an enzyme, if they ask it. For example, here, what are the types of reactions that are catalyzed by these enzymes? Again, I really don't think this is going to come up, but you know this is an enzyme because of the ACEs. Okay. And it says oxidoreduct. What does that mean? Redox reaction, because you have oxidation and reduction. Transferases. Okay, transfer functional groups. Hydrolysis. Lysis. What does that mean? Removal of hydrolases. Isomerases. Intermolecular arrangement. Ligases. The union of two molecules. Ligands. Okay, so super self-explanatory. I don't think it means anything. Okay, Vmax. This confused me. I don't like it. Vmax is maximum, what's it called? rate of activity of an enzyme. Okay, so imagine the maximum velocity at which the enzyme can work. Okay, and then it plateaus at one point because it can't have more than that. Done deal. This is the graph. So it increases with substrate concentration, but at one point it cannot increase no more because it cannot have any more active sites to bind to these substrates. So that's all. Then we go Km. What is Km? Half of V max. Why is it written like that? This fancy guy whose name starts with K, whatever, he made that. Okay, I think it's like Linear Michaelis and something like that. Anyways, Km means half of V max. Okay. You don't need to know all this. Okay, really does not matter. But you need to know that it's the half of the V max. Okay. Why do you need to know this? To understand how the graphs work. So we have inhibition. Inhibition means something that stops something else. We have three types: competitive, non-competitive, uncompetitive. We're going to get into it. Competitive, imagine I have a spot for something to bind to, like this, okay, but something else binds to it, right? So it inhibits activity. Okay, what does this mean? If this inhibitor wasn't there, the Vmax is still the same? Yes. But the Km is higher now. Okay, and we're going to see this right here. The Km is increased while the Vmax is unaffected. And this is a graph that you could see it. Again, you might not need to really understand this graph, but you need to know that. Competitive, okay, I want to bind here, okay, this is the substrate. But something else comes and binds here, does not let me bind. Then when it leaves, with more substrate concentration, I get in, right? At the half, so more substrate is needed at the halfway point of the velocity to make everything work. But if we're at the max velocity, it's the same. Remember that. Then, non-competitive enzyme inhibition means we have an allosteric site somewhere other than the active site where this thing binds to. Okay, and what does this mean? Very simple. The Km is unaffected because it goes at the same speed. But because that inhibitor is still there, it inhibits the max volume because it'll always be there. It won't let go, right? Competitive inhibitor, okay, it binds, reduces the Km because it reduces the speed, and the substrate value needs to be higher to overcompensate for this. But once it's gone, then everything else can bind normally and reach its maximum potential. But here, non-competitive, the inhibitor is allosteric. It binds somewhere here, and it just makes everything slower. Imagine like a child pulling your leg, right? Maybe it won't stop you from eating, but it'll definitely make you slower at it because you have something pulling on your leg, right? That's that. So the Km is unaffected because the same amount can go in and out, right? But the Vmax is reduced. And why is this? This is because we have an inhibitor that's not at the active site stopping things. Lastly, we have uncompetitive. What is uncompetitive enzyme inhibition? This is where we have the active site and something binding right here. Okay, so it binds to the enzyme substrate complex. This whole thing's called the enzyme substrate complex, right? So the place where the enzyme and the substrate meet, that's the complex of it, which does not allow for the product formation. So for example, I have my little substrate, okay, the reactant, let's say, comes into the active site. Then an inhibitor comes here and stops it because it's pushing it, doesn't let it leave after the product is formed, right? So what does this do? Not only does it reduce the Km, because remember, it's at the active site and it's an inhibitor, so reduce Km, just like competitive, but it's kind of on the outside and it's always inhibiting because it binds really, really tightly, so it reduces the Vmax. That's a graph of it, and that's it, right? So reduce, reduce. Now, just to look at the graphs one last time. what did we say? This is all backwards because this is 1 over V 1 over S. So we said inhibitors like this, always no inhibitors like this. This is, let me get the annotation thing. This will always be steeper, okay, than this. Right? Why? Because Km is increased. Then, non-competitive is, again, more, but it starts at the same point. So we hit first, boom, boom. Then now we have boom, 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 boom. And lastly, what are we going to have? Boom, 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 boom. Right? So, not only is the Vmax reduced, but the Km is also reduced. Now we're going to do test questions, and that will be it for this lecture, and I hope you guys do well in your SATs. I hope I do well as well. Says, the catalyst functions by lowering the activation energy. Right? That's what it does. So, lowering the energy of the reactants? No. Why? Because they go like this. This is the energy of the reactants in the graph. This is the activation energy. Depending on if it's endo or exothermic, this is exothermic. And the products. They have constant energies. Okay? Then says lowering the energy of the products, doesn't do that as well. Increasing the equilibrium constant, doesn't even do that. Decreasing the rate of the reverse reaction, doesn't do that. Providing a reaction path with lower activation energy, that's the whole point. Catalyst, activation energy. Okay, which of the following statements is true? A catalyst increases the rate of reaction by making the reaction more exothermic. Nothing to do with that. Lowers the activation energy. Heating a reaction mixture increases the rate. Heating a reaction mixture increases the rate by decreasing the number of reactants with the minimum energy needed to react. No. The transition state is the lowest energy structure between reactants and products. Okay? The activation energy is reduced when the temperature of a reaction mixture is increased. No. A catalyst is used in one step and regenerated in the later step. No. It's C. Let me just quickly check. So, a catalyst increases the rate of reaction by making the reaction. No. Heating a reaction mixture increases the rate by decreasing the number of reactants. No. The activation energy is reduced when the temperature of a reaction mixture is increased. No. A catalyst is used in one step and regenerated in a later step. No. A catalyst is just always there. And the transition state is the lowest energy structure between reactants and products. Yeah. What does it mean by lowest energy? It means, in theory, the highest energy, because it's getting to the highest energy before it becomes stable, right? Done deal. Find the wrong answer for the enzymes. Enzymes speed up chemical reactions. They do. Enzymes increase activation energy. No. They're catalysts. That's the whole point. You know what I mean? So, activation energy, catalyst, activation energy, right? So, that's normal, for example. That's enzyme, right? This is the whole point of the catalyst, lowering the activation energy. All the ones are correct. Here it says, in a reaction catalyzed by a given enzyme, the addition of an inhibitor resulted in changes in both Vmax and Km. What's that? Uncompetitive inhibitor, because competitive was just Km was reduced. Non-competitive is Vmax is reduced. And both is uncompetitive. That's all you need to know, and that is it for chemical kinetics. And yeah, good luck on your exams, guys. Bye-bye. I don't want you guys to make the same because it did not make sense to me. So, in test question 2, it says a catalyst increases the rate of reaction by making the reaction more exothermic. It doesn't do that. That's correct. Okay? Does not do that. Heating a reaction mixture increases the rate by decreasing the number of reactants with the minimum energy to react. That is actually true. Sorry. No. D is, what the fuck? What's the answer? Okay. Alright guys, so I realized that I actually made a mistake in test question 2 when I was going over it. And I just wanted to tell you guys. Now I said my goodbyes, I'm going to say it again. But pretty much, in test question 2, I was wrong. And I don't want you guys to make the same mistake. So it says a catalyst increases the rate of reaction by making the reaction more exothermic, right? It does not do that because the graph goes like this, okay? Activation energy does not depend whether the graph goes like this or like this, okay? That's that. Now it says heating a reaction mixture increases the rate by decreasing the number of reactants. It does not decrease, it just gives more energy, so more collision theory, whatever. So false, false. The transition state is the lowest energy structure between the reactants and products. That is actually false. What did I say before? It has the highest potential energy. And this can be seen in the graph. How? I draw it for you. This is the graph. This is increasing energy. Okay? Does not matter. This, don't even think about here. Okay? You go react. You have reactants. Activation energy. Let's say this is exothermic. Okay, whatever. Products. This is the highest point, right? This is the transition state. And this is the highest point and highest potential energy, right? Because energy increases by this graph. Done deal. So that makes sense. So that's false as well. Then we're going to do E. A catalyst is used in one step and regenerated in a later step. When we take the car example, let me go to it. Okay, does the platinum just disappear? Does it get used up and then it just somehow comes back? No. A catalyst is something that is just always there, okay? So, it's the beginning of the reaction all the way to the end. It's not something that gets regenerated and stuff like that, okay? So, this is also false. Now, here says the activation energy is reduced when the temperature of a reaction mixture is increased. Why? Activation energy is reduced because we're inputting more energy, compensating for the activation energy, and therefore this is the correct answer. So that's all I want to say. Again, good luck on your exams, and yeah, bye-bye.